Yes, I knew it. I always suspected. Okay, so number 26. Could someone shut those guys up in the back for me, please? All right, so 26, you got this incline, double incline. They have different angles. The one on the left is 20. The one on the right is 30. There's a pulley in the middle. The one on the left is 10 kilograms. On the right is 12 kilograms. And it asks for accelerations, force vectors. That's it. Okay, well, normally when you have a system, yes. Okay. Normally when you have a system of things and you're trying to calculate the acceleration, you isolate everything together. That's the easiest way. But here, that isn't probably the easiest way, because if you represent these in the same coordinate system, the accelerations of the two things are different. And so in this one, we're going to isolate the two parts individually and then solve a system of equations. Okay, yes? Nope. No, and right, so we'll use a coordinate system like this for the 10 and one like this for the 12. And I think the best way to make that make sense to you, like, how do you know whether you need the same coordinate system or a different coordinate system? Just think of it this way. We're going to use this coordinate system to come up with a relationship between variables that's true, you know? And then separately, we're going to use this coordinate system to come up with a relationship between variables that's true. And then we have these two true relationships between variables. And if they're both true, you have to be able to solve them as a system. You know? And so that's kind of the reasoning that says, like, yeah, there's no reason those have to be the same coordinate systems. Yeah. Okay, well, let's see. So free body diagram for 10. Let's do that first. We have a weight force of 98.1, a normal force N10. We're assuming no friction. And then the only other force is the cable force. Along that whole cable, we know that the tension is the same, so I'll call that T for both of them. So Newton's second law says 98.1 times cosine and sine of 250 degrees plus 0 N10 plus T0 is equal to, let's call this one A0. We know that it's accelerating along the, along the surface. Yes. We're not trying to find that normal force, so we'll just use the x equation. What's 98.1 times cosine of 250? Okay, so negative, and then I'll move it to the other side and we get 33.55. In radians, that's too bad. That's a shame. Okay, so everyone with me up through here? That's our first equation, but we can't solve it yet. We have too many variables. So now we'll go to a free body diagram of the 12 kilogram. There's a weight of 12 times 9.81, 117.73. And then there's a normal force I'll call N12. And then there's a cable force of T this way. So Newton's second law, yes. So 117.73 times cosine and sine of 300. It'll come out negative on its own, Oh, no. You just give the magnitude of it and then cosine and sine of the angle, and the sines all do themselves. Then plus 0. Yeah, because we're not using cosine and sine for that. If you could also do that as positive t times cosine and sine of 180, and then you wouldn't have to do the negative. Yeah. But yeah, when you say that that's in the negative x direction, you're doing cosine and sine yourself in your head. This normal? No, that's in the positive y direction. It's up, yeah. And then plus negative t0. And now, what's the relationship between the acceleration of 1? So if this one accelerates, if this one moves an inch in its positive x direction, this one moves an inch in its positive x direction. So in this case, those accelerations are the same. The variable representation is the same. Anybody have any questions about that? Yep. Well, actually, in their own coordinate systems, they're the same. If you did them in the same coordinate system, they'd be different. And then the x equation for this says negative t minus 12a is equal to, what's 117.73 times cosine of 300? Negative 58.86. And that's our second equation. So now we have this system of two equations to solve, and it'll give us the tension and the acceleration. So T minus 10A equals 33.55, and negative T minus 12A is equal to negative 58.86. You can just add up those two equations and the T's cancel, and you get negative 22A is equal to negative 25.31. And then what do you get for A? 1.15 meters per second squared. Plug that back into the system, and what do you get for T? 45.06, I'll call it newtons. Then the acceleration vectors for each of them in their own coordinate system are 1.150. And the force on, let's say, on the 10 by the cable, you can get from plugging that tension we just got into Newton's second law for the 10 kilogram. So that's 45.060. Their own coordinate systems is fine. You've spent a lot of time then.
Well, it wasn't a lot of time, but like I plugged them in.
Yeah. Yeah. You always get to choose the coordinate system unless one's specified for you in the problem. So. Any questions about that one? All right, and then 29. That one looks hard.
Wait, one question on 28.
28.
So I did it, and it comes out with the negative acceleration. But it seems like the elevator is going up because the spring is stretched, and so then that'd be a positive acceleration. And then I was like,
oh,
is that then Newton's
third
law, or like,
okay.
What is it asking for?
So if it's just hanging and not accelerating at all, that spring is going to extend longer than its resting length. So what your answer says is that hanging, it would be longer than 7 centimeters.
Okay.
And then you have to accelerate up to make it shorter.
Okay, got it.
Yep. Of the elevator, I think. Well, both, because in all these spring problems, we're assuming that the forces and accelerations are constant, and so the thing isn't oscillating. And so the whole thing is moving as a system, and all that acceleration is doing is determining how far the mass is from the ceiling. I don't remember.
Yeah, it was.
Okay. Okay, so 29. So this one we have to do all symbolically. Yeah, that's a pain.
So it says using these variables, but there's no.
Yeah, you're right. That's funny. Yeah. I guess that's right.
Wait, so that.
What I should have asked is how long the spring is, but I never asked that. Yeah. Yeah, you're right. If it doesn't ask anything about the length of the spring, then nothing, the spring doesn't even matter in this problem.
Then how do we find that tension, that force on M1 by the spring?
Okay. Well, we're always in these problems assuming that all the distances are constant, all the forces and accelerations are constant in these spring problems. So the spring just does the same thing a cable would do.
What? That's what I'm saying.
That's my mistake. I mean, I didn't mean to make that like, because, well, yeah, we do need to deal with the friction. Okay, so maybe we should calculate how long the spring is, because it's sort of unsatisfying to.
Will we get our exams?
I haven't graded them yet, so,
Okay.
and I'm going to be pretty busy lecturing, so probably not.
Okay.
But tomorrow, no doubt the scores will be up. Yes. Yes. Yep. So that's my number one thing on my agenda tomorrow. And the lab test too, everything posted tomorrow. Or my name isn't Hiram G. Bullock. That's just how it's set up.
Is the one hanging down and no, I mean on my phone. That's a darn good wheel you got.
Thanks. That kind of wheel is called a pulley.
Yeah, wait, our wheel and axle and pulley.
Wheel and axle.
Wheel and axle.
Really?
Is
They're technically
machine and
separate.
pulley is exactly.
It's the same idea, yeah. But we do have to deal with the friction on the,
Yeah, but
not on the pulley, correct. To show that that's a surface. Okay, who's ready? All right, well, let's start out with, so I'm going to start out with a free body diagram of the hanging mass. And then I'm going to do a free body diagram of, maybe I'll do the individual ones, I guess. All right, well, let's start with the hanging mass. That's always a good place to start. All right, so we have a weight down of M3G and a force up of T. And so Newton's second law, the only one that matters is the Y component, says positive T minus M3G is equal to M3 will have the default be that this is accelerating up. And so our first equation, I'll number these equations, says T minus M3A is equal to M3G. And I rearranged it like that because T and A are variables. M3 and G are not variables. Those are constants. Okay, we're not trying to solve for those. We're trying to get the other stuff in terms of those. Okay, That one was good. That one went great. So now let's isolate M1. So that has a weight force of M1G. Oh, and for these, let's use, so I'm going to use this coordinate system for this one. And our incline coordinate system for the other two. No.
You haven't gotten to it yet.
Yeah, and so then there's the normal force. I'll call that N1. And for the friction, you know, this one has a couple of problems. We need to know one more thing in order to do the friction force. What do we have to know? Right, but it gives us mu, but we don't know what direction the friction force is acting if we don't know what direction this is moving.
Like A is moving down and B is moving up.
It does say that?
Yeah.
Oh, okay. Oh, good.
We do.
Yeah. Okay, so if the hanging mass is moving down, which way are the sliding masses going? Yeah, they're in the negative x direction. They're moving. And so the friction force is down the incline. Right. And so the friction force here is mu times N1. Then we have the tension, the same as the other tension. And then we have this other force, which is the spring constant times delta L. Okay, this one didn't go quite as smoothly as the first one. This one's a mess. But yeah, the K, right. The whole thing is the spring force. K is the spring constant.
Because we weren't given those variables to work with. Like it said using these variables.
Yeah.
Give us
this problem.
Wait,
anyways, this is how you have to do it. You need to know that. So we got negative T0 plus 0N1 plus mu N1 0 Nope. That the force applied by that cable is the same to everything that cable's attached to, and the direction is just parallel to the cable away from the body. Well, yeah, but we deal with the acceleration on the right side of Newton's second law. Here we're just putting all the forces in. And then we have K delta L 0. And we still have to have the weight. So in this case, that's equal to, if you do the trigonometry, just to simplify it a little, M1G times the sine of theta, and then negative M1G cosine theta. Okay, running out of room. It's yeah, it didn't. I'll have to draw that again. Your paper doesn't do that?
Is that just a MacBook or a Mac?
It's a Lenovo Yoga 12 tablet. It's pretty old. Yeah. If I was just going to use, so yes, you could do it as positive M1G cosine of 270 plus theta, positive M1G times sine of 270 plus theta. To get the 270 out, I just like made a right triangle and did the trigonometry myself. You could just as well write this as M1G cosine of quantity 270 plus theta, M1G sine of 270 plus theta. But just to simplify it a little bit, I thought of this triangle like this. Let's see. So we have the downward force of M1G. These are the two components. This angle's theta. And so now just use SOHCAHTOA and you can figure out what those two components are. So that's how I got that. And all this is equal to the mass M1 times the acceleration A0. That's what I was just talking about for 4 minutes. Well,
He was explaining that if you add 270
so
cosine,
so if you think of this triangle this way, okay. Then the x equation says negative t. Yep. Okay, so the y equation says n1 is equal to m1g cosine of theta. Plug that into the x equation. You get negative t plus mu m1g cosine theta plus m1g sine theta is equal to m1a. Did I leave that out? Plus k delta L, okay, 1, 2, now I have all those, is equal to M1A. And so our second equation looks a lot worse than our first equation. And it says negative t, and I'm going to put all the stuff with variables on the left side of the equation and all the stuff that's just constants on the right side. So negative t plus k delta L minus M1A is equal to M1G times the quantity I guess negative m1g times the quantity mu cosine theta plus sine theta. Okay, so now we have two equations. Let's think about what variables we have so far. Maybe we can solve for something. So from equation 1, we have the variables t and a. Everything else is constants. From equation 2, we also have the variable delta L, and that's all. So we have two equations for three variables, so we can't solve for anything yet. Keep going. So free body diagram for mass 2. Yeah. Okay, and the force down is m2g. The normal force is N2. And then the spring force, the default is always to treat that like it's a tension. And then if it's a compression, that'll come out in the answer. So I'll write this as K delta L. And so Newton's second law says negative K delta L 0 plus 0 N2 plus M2G sine theta negative M2G cosine theta is equal to M2 times the vector A0 and so the X equation says negative K delta L plus M2G sine theta is equal to M2A, and that gives us equation 3, which says negative K delta L minus M2A is equal to negative M2G sine theta. Yeah.
How can we assume that acceleration is the same as the other one? Because I know it's connected, but
Right.
like usually
With the spring, you mean?
If you have something with the spring and you move the front thing, the second is like sometimes slower to accelerate.
So, right. So for any of these problems with springs where we're asking for accelerations, we're assuming that there's no oscillation going on. Everything is constant, and we're just trying to figure out like how far apart these are as a result of that acceleration.
Okay.
So oscillation problems are separate, and I don't think I gave you any of those. I just gave you that one example. So we're always like, if you think about also the case of the thing connected to the spring that's swinging around in a circle, and also if you started it swinging, it would start doing this wacky oscillation thing as it was going in a circle. But we're assuming that it's all in a steady state.
Okay. So we can assume that that's the same A as.
Right. Yep. All right. Well, so now we have three equations for three variables. Those variables are T, A, and delta L. And obviously then it's a sort of painful algebra process to come up with those, but it's not hard, it's just tedious. That's what I'm going to do, but you should not do that.
If we didn't,
Well, actually,
use the spring constant and all that stuff,
yeah,
because it wasn't very given.
yes, that's true. So yeah, I don't. As far as right, this problem was a mess. If you didn't do it, that's okay with me. You should try to understand how this works because these are all, it's solidifying topics that are important. So now we're going on to the next topic. Momentum, linear momentum. Yes. Yeah, exactly. Oh, yeah. Okay, so linear momentum. There's also an angular momentum, so that's why we're saying linear. And momentum is the mass times the velocity vector. And this is a pain, but we're going to call it lowercase p. So this is, I think, the first time in this class that we've had the same representation of two different quantities. Usually we use p. Yeah, maybe. But so this p vector now stands for position vector and momentum. And so you have to be clear in a problem about which one it's talking about. So if you think about the mass times the velocity, you can think of the magnitude of momentum tells you how much it would hurt if something ran into you. How much it would hurt if that thing ran into you. Football coaches are interested in finding the people who can create the largest magnitude of momentum. You want a big person who can run really fast because you want to hurt people. Yeah. Yeah, but that's true, but that's not being addressed here. And here's how momentum comes up. You can think of Newton's second law as saying that the net force is equal to the time derivative of the momentum. And in fact, that's the way when Newton came up with this law, that's the way he was thinking about it. And so this leads to, if you integrate, yep. But we've been talking about it in terms of acceleration instead. if you integrate this with respect to time, gives the two results that we're going to use. What, from what? Position and momentum, you mean? No, people don't. It's a pain. You just have to know what you're talking about from the context. Yeah, it's not great. But they only have 26 letters. You know, that's, I guess, the problem.
They have Hebrew letters.
The Greek letters usually stand for angular stuff. Yeah, yes, yes, I agree. But I just want you to know that I wasn't the one who made this decision. This was made long before me. And it doesn't even stand for like why not M vector, at least, you know? We have an M, but it's not a vector, and at least momentum starts with an M. I don't know. But if you integrate this, so this form of Newton's second law, if you integrate this with respect to time, you get the two results that we're going to use. The first one says that the change in momentum over the interval of time that you're integrating is equal to the integral from, let's say, t1 to t2 of the net force as a function of time dt. This is called the impulse. And this whole equation is called the impulse momentum equation. And then the second way that we'll use this is if there's no net force, then the change in momentum is zero. And this equation is called conservation of linear momentum. And if you remember this, it's always really easy to tell when when it's useful to go into a momentum approach for a problem. So when, and up until now, there's kinematics and kinetics. You use kinematics if no forces or masses come into the problem. You use kinetics, Newton's laws, if forces and masses come into it. But now, starting now, we're going to start to have, like, problems will come up, and we're going to have multiple approaches we can take. And you have to be able to tell, like, what's the benefit of going this way versus this way. So this one is pretty easy if you remember this. It's pretty easy to know if you want to go towards momentum. These momentum equations are useful for collisions and explosions, more often collisions. Well, I mean, you can use these equations if you're trying to figure something out for, like, what happens in an explosion, you know. Yeah, right. Okay, so if you see a problem and it deals with a very short duration of time, impact between things, or an explosion, you know that you're going to use the momentum equations. All right, so I'm going to start with the impulse momentum equation. Yeah, that's a good idea. We're not going to use this one too much, but I need to show you how it works. This is usually the way to make this useful is to we'll assume that over the time interval of the collision, so during the collision, the contact force is constant. So let me just give an example, and then we'll go on to the next thing. So here's a bat. You can tell it's moving fast because it's bending. That's a trick I learned from Dr. Seuss. Okay, and this ball's coming in with a speed of 40 meters per second. At an angle of 5 degrees with the horizontal. No. And then there's the impact, and the ball leaves the bat at 50 meters per second. At an angle of 30 degrees above the horizontal. And we're going to use a coordinate system with the y-axis up, the x-axis horizontal. What's the average contact force if the contact lasts 0.008 seconds, so 8 milliseconds? All right, well, the impulse momentum equation says that the change in momentum, which is the momentum at the later instant minus the momentum at the earlier instant, is equal to the integral of F net as a function of time dt. And if we're trying to calculate the average contact force, then we're going to assume that this is constant. Okay, so if we're going to assume that this function is constant, well, this one, the key is that we're asked for the average contact force. And if you're asked for the average, that's the same as assuming that that force is constant. And that's the only kind of problems we're going to do. So we're always going to do this. But if you did know something about that function, you could put more detail into that. You could also, assume that this is a linear function, like it starts out at 0 and ramps up to a maximum or something. But we're going to always assume that it's constant. And so if it's constant, you can pull it outside of the integral. And you get that P2 minus P1 is equal to this constant F net times the integral. We can think of this as from 0 to 0.008. And now we can use the I need to give the mass of the ball. The mass of a baseball is 0.145 kilograms. Okay, so what's the momentum at instant 2? The mass is this. The velocity comes from the angle and the speed. So P2 is equal to 0.145 times the velocity of 50 times cosine of 30, 50 sine of 30. And that gives 6.279 for the x component, 3.625 for the y component. These units are kilograms, meters per second. At instant 1, the mass is 0.145. The velocity is the velocity is 40 times cosine and sine of 185 degrees. And that gives negative 5.578. And then negative 0.506. And so now put this together and you get 6.279, 3.625 minus negative 5.578, negative 0.506, is equal to F net times 0.008 minus 0. That's what you get from the integration. And you get that F net is equal to 1482.1 for the x component and 516.4 for the y component. This is newtons. Okay, so if you know something about the velocities before and after, and you know something about the duration, you can figure out something about the force. This isn't the contact force yet, but because we have to subtract out the weight. But you can imagine that the weight of that ball is a pretty tiny force compared to this net force. And so a lot of times people just ignore that, but we can subtract that out. You have a question, Colton? Okay, so we are calculating, so the object that we're looking at is the ball. So we're calculating the force vector, the net force vector acting on the ball. And there's two forces acting on the ball if you draw a free body diagram. Yeah. So I was going to now do the free body diagram, and you know, the weight is going to be this tiny little force compared to the contact force. And when you subtract it out, it's going to be something close to this for the contact force. But we have, yeah, right. So the weight is 0.145. Can someone calculate that? 0.145 times 9.81. So 1.42. And then we have this contact force, force on the ball by the bat. And those two added together so that plus 0, negative 1.42 is equal to that net force. And so the force on the ball by the bat, the contact force that we're looking for, is 1482.1 in the x direction and 517.8 in the y direction. You can imagine something like that would be useful to know if you're, building a bat. You need to know how much force you're likely to have to deal with without that bat breaking, and that's the kind of thing the engineers are looking at. Yes, when they try to determine how thick to make the aluminum in the bat or whatever. Yes. Two vectors for force. So we got the F net, and it makes sense up to there. And then we went to the free body diagram of the ball while it's in contact with the bat. And there are only two things acting. There's the bat acting on it, and then there's also gravity, because gravity's always acting on things. And so we just added up the two individual forces that are acting, set it equal to the net force, and then figured out what the contact force was from that.
Like, why does it look like a coordinate system when you're showing?
Because we don't know the direction. I see what. So think of this as these are two separate forces. A horizontal component going this way and a vertical component going this way. And I'm just representing those as a unknown force vector. I could have written that as F and R or something. But either way, we know that the bat's applying a horizontal force and a vertical force. Any other questions about that? Let me give you one to work on. Oh, yeah. So let's do another one and see if you can work through this. So a 50-kilogram person jumps straight up. During the jump, the contact with the ground takes 0.2 seconds. And immediately after leaving the ground, the person's speed is 2.5 meters per second. What's the average contact force between the feet and the ground? Okay, so see if you can figure that out. Go work on the board. So we know that the momentum at instant 2 minus the momentum at instant 1 is equal to F net times the integral from 0 to 0.2 dt. We know that because we're assuming that F net is constant, because all we're looking for is the average. At instant 2, the momentum is the mass times the velocity of 0, 2.5. So that's 0, 125. At instant 1, the person's starting the jump, so the speed is 0. And so this is just 0, 0. And so we get that 0, 125 minus 0, 0 is equal to F net times 0.2. And so F net is equal to 0, 625. That's the net force, that's not the contact force. In the baseball case, if you made the assumption that the net force and the contact force were pretty close to the same thing, you would have gotten a good answer. In this case, those answers are pretty far apart, and it mostly has to do with the duration of the impact. You know, a jump takes a long time. You're not changing those velocities instantly, you know. So during the process of jumping up into the air, we have a downward force of 50 times 9.81 So that's 490.5. And then we have the contact force. That's the normal force. And those two forces add up to the net force that we just calculated. So 625 is equal to 0n plus 0, negative 490.5. And the y equation there says n is equal to 490.5 plus 625 is 1,115.5 newtons. And so that contact force is 0.1115.5. At this part, he's accelerating up so that he can jump off the ground. So that force, the ground is pushing up on him to launch him into the air. And so the duration of this impact has a lot to do with the average force. If you had two, just let's think of these two, like two steel balls are hitting each other and they're bouncing off each other, and they start out going 1 meter per second, and they are going 1 meter per second when they bounce apart. And let's say they're steel, they're not very flexible. Let's say we assumed that those are perfectly rigid as an approximation. So if these two perfectly rigid things bounce against each other and this one goes from 1 meter per second this way to that way, what's the average force in that collision? Well, if they're perfectly rigid, there's no period where they deform and, spring apart. And so the duration would be 0. And so that force would be infinite. There's no such thing as two perfectly rigid things bouncing against each other and springing apart in no time, Anybody have any questions? Okay. Well, I will see you a week from today. You have math on Wednesday, and then Friday I'm going to give Roger some problems for you to work on, and he's going to be the one there. Oh, and it's going to be here on Friday. Don't forget that. Yeah. So it's not in the lab, it's here. So you're meeting in this room on Friday.